In this video, we will be talking about probability and the very basics of probability, mostly vocabulary, and some facts maybe about probability and how it works. And then we will get into some examples on how to actually find the probability of some events. And as far as I can recall, we will just be sticking with events that are equally likely for this particular video, maybe except for the very last example. Let's get to it. So here are the four major vocabulary words that we will be looking at in this video. We have probability, the main idea of this entire video. This is a measure of how likely an event will occur. Well, we need to know what the word event means in order to fully understand what's going on here. So an event is the action of obtaining a specific outcome. Well, okay, what's an outcome? Well, an outcome is any possible result of an experiment. And so this leads me to define experiment. The experiment is any occurrence for which the outcome is uncertain. So some of the prototypical examples of what an experiment is would be flipping a coin. We don't know what the outcome will be when you flip a coin. You could either get heads or tails. So those specific examples, heads and tails, those possible results of an experiment, those are the outcomes. You can either get a heads or you can get a tails. But the difference between an outcome and an event is we can record outcomes, but we can't record the outcome without actually flipping that coin. And that flipping the coin is the action of obtaining whatever specific outcome we're looking for. So the experiment is we will flip a coin. The outcomes we can possibly get are heads or tails. The event that we would be looking at would be the actual event, the actual action of flipping a heads or flipping a tail. And then we can calculate probabilities based on all of that. So let's move on to some more facts about this probability here. All right, so here are some facts on probability. The probability of an event, and yes, we will only be looking at the probability of events. That's the entire point of probability. Will always be between 0 and 1. So I've got a few notes here. When the probability equals 0, we call this the impossible event. And when the probability equals 1, there are a couple different ways this could be said. This could either be called the certain event or the sure event. It is sure to happen, or it is certain that this event will happen. And so here's a nice little table to explain all this. So on one end of the spectrum, we have the impossible event. There's no chance that happens. There's 0 chance that it happens. And on the other side, we have the probability 1. It is absolutely going to happen. We're certain or sure that it'll happen. So if any value probability ends up between 0 and 0.5, we call that less likely. At 0.5, that means there's a 50-50 shot that it'll happen. And if the probability is between 0.5 and 1, we call that probable, or you can say more likely to happen. So just to give you an idea of what numbers we'll be looking at, just decimals and absolutely fractions between 0 and 1. In addition to that, we will actually be looking at 3 different types of probabilities. We will have empirical, theoretical, and subjective. Now, for most of the time, we concentrate here on the theoretical probabilities because that is exactly what we like to have happen, and it doesn't take a whole lot of time. And that is like in a perfect world, what would the probabilities be? If you're flipping a coin, there's a 50% chance you'll get a heads and a 50% chance you'll get a tails. Whereas when you start looking at empirical probability is actually performing the experiment over and over and over and over and over and recording your results and taking the probability based on your results. So that takes a lot more time because you actually have to run the experiment. So when I said, the theoretical probability of flipping a coin is 50% heads and 50% tails, maybe you flip a coin 1,000 times, and that would take a very long time to do, but you only get 49% heads and 51% tails. It doesn't play as cleanly, as nicely as theoretical probability does. And the last type of probability we will look at is a subjective probability. And this is an estimated probability based on your experience or intuition. The example I like to give is, since I live in the Houston area, what is the chance that the Rockets or the Astros or the Texans win their next game? If you are a fan of these teams, you will probably have a higher probability than people who are not fans of these teams. So it's just how do you feel? What do you think the chances are that an event will happen? Okay, I believe this is the last slide that will just pepper you with a bunch of information. First, we have the counting principle. And so very quickly, if a first experiment has m different outcomes and a second experiment has n different outcomes, then the two experiments in that order can be done m times n different ways. Or the other way of saying that is those two experiments in that order has m times n different outcomes. And I'm going to do an example of this on the next slide just so you can see what's going on with that. But quickly following this definition, I have the definition for sample space. And sample space for an experiment are all the possible outcomes for an experiment. So when we start computing probabilities, we will need to know exactly how many different outcomes there are for that experiment in order to start figuring out the probabilities of an event. And then we have this idea called a complement. The complement here is the probability that an event doesn't occur. That is the complement of the probability that the event does occur. And we can find the probability of that by subtracting the probability that it does occur away from 1. So if we know what the probability is that you'll roll a 6 on a 6-sided fair die, we can find the probability that you don't get a 6 pretty easily. We can just do this little subtraction here. And the last thing here, equally likely events. Equally likely events have the same probability of occurring. So this is when you flip a coin, or you roll a die, or you pick a random card out of a deck of cards. Those are the 3 prototypical examples you'll see in a probability unit. These all have equally likely. These are all equally likely events in their own scenarios. Like flipping a head is the same as flipping a tail. They have the same probability, 50-50. All right, let's get into an example of what the counting principle looks like and how it works. So in this example, we're going to match up shirts with ties. And so as you can see, there are 3 different shirts and 4 different ties. It was hard to draw a white tie. But pretend there's a tie here. Let me see if I can do this, right? Let's see, there's a white tie. Fine, I just won't fill it in. All right, so that's a white tie. And what we're trying to do is we're trying to figure out how many different ways you can pair up these ties with these shirts. So what I'll do here is I will say the shirt here we can call BA for black, R for red, and BL for blue. And for the ties, I can use G for green, I can use P for purple, I can use Y for yellow, and I can use white for or W for the white tie. So the first thing that comes to mind is I could take any one of these ties, right, and pair it up with 2, 3, 4, pair it up with this black shirt. So I could say, let's see, we have black, black, we have black, and we have black. So I could say I could pair it up with the green tie, I could pair it up with the purple tie, I could pair it up with the yellow tie, or I could pair it up with the white tie. So right now, off the bat, I see there are 4 possible ways I can do that. Well, my goodness. Now, if I go back and look, I can say we can do that same thing. We can do green and red, purple and red, yellow and red, and white and red. Okay, so I can list out 4 more: red, 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 red. And I can have, what here? I can have red with green, I can have red with purple, I can have red with yellow, and I can have red with white. Okay, well that's 4 more ways. And lastly, I know I have this blue shirt, and I can do the same thing there. Oh my goodness. So blue, 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 and blue. So I can pair the blue shirt with the green tie, I can pair the blue shirt with the purple tie, I can pair the blue shirt with the yellow tie, and I can pair the blue shirt with the white tie. So I have 4 more ways that I could have done that. All right, so let's take a look here. How many different ways? We've got 4 and 4 and 4. That makes 12 ways, aka outcomes. But it just would have been so much easier, right? So the first experiment we would run is picking a shirt. And so how many different ways could we have picked a shirt? Well, we could have picked a shirt one of 3 different ways, right? We could have picked black, red, or blue. Times how many different ways could we have picked a tie, right? The second experiment would be picking a tie, and we would have one of 4 choices there. 1, 2, 3, 4. Green, purple, yellow, white. So if I had taken the number of outcomes in the first experiment of picking a shirt and the number of outcomes in the second experiment of picking a tie and just multiplied them together, boy, I would have been able to make that happen a lot faster just by multiplying them. And this is a really good idea here because we want to be able to do this quickly. Because, I mean, most people will not only have 3 shirts that they can wear. Most people will have maybe 10 shirts they can wear. And I myself have about 30 ties. So could you imagine trying to come up with every combination like this where you have 10 shirts and 30 ties? I wouldn't want to do that. So instead, what I could do to make this quick is say that I would have had 10 shirts times 30 ties, which would have given me 300 possible outcomes in this situation instead of actually writing down all 300 outcomes. So understanding how the counting principle works makes it very easy to start finding out how big the sample space is. So we don't necessarily need to know all of the outcomes. All of the outcomes listed out like this, these 12 outcomes are the sample space. And most of the time, we don't need to know what each individual outcome looks like. We will just need to know how many outcomes there are. Another way of saying that is we just need to know how big the sample space is. Once we figure out how big that is, then we can start taking the probabilities of events. So on this slide, we will talk about exactly how to find a probability. of a particular event. So we will talk about the probability that the event A occurs. So you can see here in the notation, the capital P tells you that we are trying to find the probability of what's inside this set of parentheses here. And this event A will be more specific when you get into more specific examples, like a six-sided die is rolled. And how you find this probability is you find out the number of ways that event occurs, and then you divide by the total number of outcomes, or the size of the sample space. So in this example down here, I want to start out with the actual sample space of this experiment. Right, so we have an experiment. All of the possible outcomes are what create the sample space. So if you roll a six-sided die, the only choices you get are these right here. You can either get a 1, 2, 3, 4, 5, or 6. So this is what I am going to call the sample space, and this has 6 outcomes. And that's it. We have a total of 6 possible ways that this experiment could go. So one probability we could look at would be, what is the probability you roll a 6? And this can be shortened. You'll see maybe just the probability of getting a 6. So these two things mean the same. It's just this is a little more wordy. So it might be a little more understandable, but eventually we will start shortening it to this. So you understand what this means. The probability you get is 6. Well, okay, so let's say you roll this die, and our goal is this right here. There's only 1 6 in this entire list, right? So the way we can get a 6, the number of ways we can get a 6 is only one way, right? That's if we roll a 6. Now the total number of outcomes whenever you roll a die are 1, 2, 3, 4, 5, right? We have 6 outcomes here. So I have to take the 1 6 that we could possibly get and divide it by the total number of outcomes. So the probability that you roll a 6 would be one way out of 6 possible outcomes. There's the probability right there, 1 over 6. Let's take a look at a different one. Let's say we want to know the probability you roll an even number. Okay, well, the probability that you roll an even number, well, we're going to have to come up here and look at our list. How many ways are there to get an even number? Right, so we can look here, it's 2, 4, and 6. So I count 3 different ways to get an even number. How many different outcomes could you get, right? We have to divide this by how many total outcomes there are available for us to pick from, and that is 6, right? The sample space size, that is 6. Okay, so now I have 3 out of 6, and if you leave this as it is without simplifying it, you're wrong. You've got most of the idea, but this can be simplified. 3 over 6 can be reduced to 1/2. And if you think of it, that makes a lot of sense, because half of the outcomes are even and half of the outcomes are odd. So you have a 50-50 chance of getting an even number. Let's see. What happens, let's see, what's the probability here of getting a 10? Well, we have to go back and look. Since we're only rolling a 6-sided die, our only outcomes are 1, 2, 3, 4, 5, and 6. There are no outcomes that give you a 10. So there's no 10 in our list of outcomes, and there are 6 possible outcomes. So 0 divided by 6 would be 0. There's no way you can get a 10. I think that makes sense. You can't roll one die and get a 10. The last example I want to do here, I'm going to do it off to the right. Let's say the probability you get a number that's less than 6. So a number that you get less than 6 would be, well, let's come up here. What numbers are less than 6? Well, we have 5, we have 4, we have 3, that's less than 6, 2, and 1. So I have 5 possible choices here now. That'll give me a number less than 6 over 6 possible outcomes. And that will be my answer, 5 over 6. And that's because I cannot reduce this fraction anymore. So here are some basic probabilities based on rolling a 6-sided die. Let's take a look at some more probabilities. So on this slide, you can see we have a twister spinner. I very much enjoy this example for probability purposes as it has a very decently sized sample space, which, by the way, the sample space has 16 outcomes, and as a matter of fact, all outcomes are equally likely. And you can tell because each outcome has the same chance of happening. So we have left hand has 4 choices, right hand has 4 choices, right foot has 4 choices, and left foot has 4 choices. So let's even take this back to the counting principle, right? So we have the first experiment will be the limb that gets used, right? So there are 4 choices for limbs, and that is left or right hand or foot. So there are 4 limbs times 4 colors. Right, you could either have a color that's green, red, yellow, or blue. And that would be the 16 possible outcomes. We could even break this down more, right? So we could have 3 different experiments. The first one could be, let's see, side of body, right? You could either be left side or right side. You could have the hand or foot, right? That's 2 possible choices times the number of colors. So 2 times 2 is 4 times another 4 gives you still the 16 possible outcomes here. So it all depends on whether you want to look at this as 2 experiments or 3 experiments. Really, it could be either way. But either way we look at it, we still get the same number of outcomes. All right, so we can start asking about probabilities using this spinner. So the first one I might ask about would be the probability of, let's say, the spinner landing on a red. Well, we can go through and find out how many red spaces there are. So I see 1, 2, 3, 4 red spaces. And I know there are 16 possible outcomes. So as long as I divide these 2 things and simplify as best I can, I know there's a 1 in 4 chance that my outcome will be red. So let's bump this up a little bit. Let's say I want to know the probability of spinning a hand. So over here on the right side, I can look. Let's see. So in this left hand, I can say 1, 2, 3, 4 outcomes for the left hand, and 1, 2, 3, 4 outcomes for the right hand. So I've got 4 here and 4 here. I've got a total of 8 outcomes out of 16, which means I can then have a 1/2 chance of spinning a hand on this twister board. Now a slightly more difficult example. Let's say I want to find the probability that I get not a right foot. Wow, okay, so one way we could do this, since it is at least easy enough to count right now, I don't want any outcomes that are in this quarter of the circle. So I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different outcomes that are not a right foot. So this would be 12 out of 16. I'm going to write that over here. This would be 12 out of 16, which would be 3 out of 4 after you reduce it. And that's a lot of counting though. What I could have done instead is notice that since this word not is here, if I wanted to, I could have written this as 1 minus the probability that we actually get right foot. And that's going to be easier to count. So I will have 1 minus the chance that I get a right foot is 1, 2, 3, 4. So let's see, 4 out of 16. Now if I create common denominators, I could get 16 out of 16 for this 1 minus 4 out of 16. And then I could have just subtracted the 16 minus 4 would have given me the 12 and reduced it down to 3 over 4. But this idea that we can, if we're not looking for an event to happen, we can find the probability it does happen and subtract it from 1, ends up being a pretty powerful tool if you continue to study probability further. So I'm hoping this is clearing up a little bit of probability basics for now. On to the next idea that I forgot to put in the vocabulary / facts slides, but I think you needed to see some examples before I was able to explain this next idea. This idea here, probability distributions, it helps us look at the overall probability of all the possible outcomes happening. So for example, I want to list all the outcomes or find the sample space for flipping 3 coins. And that looks something like this. So here it goes, you flip 3 coins, you could possibly get heads, heads, and heads, all 3 heads in a row, or tails and tails and tails, or some combination of heads and tails in there somewhere. Now let's say I want to know the probability. I'm going to ask for 4 probabilities. The probability of getting 3 heads, the probability of getting 2 heads, the probability of getting 1 heads, and the probability of getting no heads. Right? And these are all of the outcomes for flipping a coin 3 times and recording the number of heads. So the experiment here would be flipping a coin 3 times and recording the number of heads. So what we want to figure out then is the probability that we would get 3 heads. This is a specific event that we get 3 heads. So that happens 1 time. We get heads, heads, heads out of 1, 2, 3, 4, 5, 6, 7, 8 different possible outcomes. So I think it's pretty easy to see this probability would be 1 out of 8. The probability that we get 2 heads, well, that can happen 3 different ways, right? We could get a heads, heads, tails, heads, tails, heads, or tails, heads, heads. So there are 3 possible ways that could happen. So the probability you get 2 heads would be, 3 out of 8. The probability of getting 1 head, like these 3 examples, or these 3 outcomes here, would be 3 out of 8. And the probability that you get no heads would be 1 out of 8. All right, so this right here is what we would call a probability distribution. We've listed all the possible ways we can get heads, either 0 heads, 1 heads, 2 heads, or 3 heads. And we've listed out the probability for each of these events. So one thing that needs to be said about this is that when you have listed out all of the possible events, right? 3 heads, 2 heads, 1 heads, no heads. The sum of the probabilities for all possible events is 1. So if you added all of these together, 1/8 plus 3/8 plus 3/8 plus 1/8 equals, well, we've got 1 plus 3 plus 3 plus 1, that's 4 plus 4 is 8. That is 8/8, which reduces to 1. This is exactly the reason we are able to use the complement rule, like in the last example we went over on the previous page. So if I said, hey, what is the probability we get not 1 heads? Well, that means we could subtract that from the probability that we get 0 heads or 2 heads or 3 heads. So 0 heads would be 1 different way, 2 heads would be 3 more ways, and 3 heads would be 1 more way, right? Because I have got 1, 2, 3, 4, 5 different ways. Oh, that's too much work. That hurts my head. I want to be able to think of it differently. Like, oh, if I don't want only 1 heads, then I could say, let's subtract the probability we get 1 heads away from 1. That's a lot easier. So I can do this, 3/8. I know that probability. It's right here, the probability I get 1 heads. That means I will have 8/8 minus 3/8, which is 5/8. And so the probability that I get not 1 heads, oh, that's so confusing to say in here, is 5/8. So I just have to have not 1 heads. That means I can have 0, 2, or 3. So 1, 2, 3, 4, 5. Yeah, it's 5/8 possible ways. So I just wanted to say on this slide that the sum of all the probabilities of all possible events is 1, and that it certainly is easier to think of in this terms when you're given a not example. So I'm hoping this clears up any bits of probability questions that you may have had at the beginning. I know this was a little bit of a long video, but there was a lot to dive into, and I hope it is now making more sense for you.